All right, let's dive right into this explainer and look at the absolutely staggering engineering required to make hypersonic flight a reality. We're talking about speeds exceeding Mach 5. At that velocity, the very air around an aircraft behaves in radically different, honestly pretty hostile ways. To pull this off, we can't just rely on the standard jet engines you see on commercial airliners today. We need a completely different breed of machine, and figuring out how to build it is easily one of the most complex, mind-bending puzzles in modern aerospace engineering.
Picture this. You're standing in the middle of a Category 5 hurricane. You pull out a single match and you try to keep it burning perfectly steady. Sounds impossible, right? Well, that is effectively what engineers are trying to do inside the combustion chamber of a hypersonic engine. It's a massive dual challenge. First, you have to somehow capture and process that ferocious wind. Then, you have to find a fuel that burns fast enough before it simply gets blown right out the back. So here's our roadmap for today. We'll start with the hypersonic propulsion problem, then compare rockets to air-breathing engines. After that, we'll look inside the scramjet itself before tackling the two massive engineering hurdles, catching the air and combusting the fuel. Finally, we'll wrap up with the future of flight. Okay, part 1, the hypersonic propulsion problem and overcoming the drag. Let's start with the fundamental physics here. The ultimate goal is flying faster than Mach 5. And doing it efficiently. When pressures and temperatures get incredibly high during supersonic flight, you just can't efficiently slow the oncoming air down to subsonic speeds for combustion anymore, which is exactly what standard jet engines do. We have to fundamentally rethink how we fight drag. Whether you're accelerating a large mass of air slowly, like a propeller does, or a tiny mass of gas incredibly fast, like a jet, generating thrust all comes back to Newton's laws of motion. You create a reaction by taking a mass and accelerating it in the opposite direction you want to travel. But at hypersonic speeds, aerodynamic drag increases exponentially, making it exceptionally maddening to achieve that net positive thrust. You need an immense amount of energy just to keep pushing forward.
Moving on to part 2, rockets versus air-breathing engines and the weight of oxygen. When we want to go really, really fast, we historically have two choices, and there's a fascinating engineering trade-off between them. Rockets are great because they're relatively simple, highly reliable, and the engine itself is pretty light. But to burn their fuel, they have to carry massive, heavy tanks of oxidizer, like liquid oxygen. They're totally held back by that immense weight. Air-breathing engines, on the flip side, just scoop their oxygen right out of the atmosphere for free. This drastically improves their fuel-specific impulse, meaning they are far more efficient. The catch? As they hit extreme velocities, their thrust drops off, and building them becomes incredibly complex. Which brings us to part 3. Inside this scramjet engine, otherwise known as the supersonic combustion ramjet.
To solve that heavy rocket problem while surviving hypersonic speeds, engineers came up with a scramjet. Think of it like a high-speed breathing organism. Notice how there are no spinning turbine or compressor blades in its internal anatomy. The scramjet just uses its own sheer forward velocity to compress the incoming air. The air violently rushes into the inlet, gets compressed by shock waves, moves through the isolator, and enters the combustor. Then, fuel is injected and ignited while that air was still moving at supersonic speeds, expanding out the internal nozzle to create thrust. It is a wildly elegant concept, but as you can imagine, incredibly difficult to execute in the real world.
Part 4, Challenge 1, air intake and catching the air at Mach 4. Here is our first major engineering battle, trying to catch the air at just the right speed. Lowering the starting speed of a scramjet is a huge deal. Right now, a scramjet needs a rocket or a secondary engine to push it all the way up to Mach 5 or 6 before it can even turn on. If engineers can lower that starting threshold down to Mach 4 or even 3.5, you drastically reduce the overall weight of the vehicle. You'd need a much smaller booster rocket, which leaves more room for payload and makes the whole vehicle safer because there are fewer complex systems relying on perfect handoffs. When you actually model how this airflow behaves, funneling into the inlet at Mach 4 versus Mach 6, it's wild. The engine has to survive intense aerodynamic shock waves. As the flow is compressed and decelerated, it creates these severe, messy non-uniformities, oblique reflecting shock waves, and tricky boundary layer interactions. Trying to feed that chaotic, violent stream of air smoothly into a combustor is a massive headache for the engineers designing this. So the secret key to starting the engine at these lower, more accessible speeds actually comes down to controlling the temperature ratio. When analyzing the flow parameters, if you look at the static temperature ratio of the flow entering the combustor, it drops significantly at Mach 4 compared to Mach 6. Basically, as this ratio goes up, the Mach number of the flow actually entering the combustor goes down. By carefully designing the inlet geometry to manipulate this exact ratio, researchers have proven that a scramjet with a starting Mach number of 4.0 is absolutely mathematically and physically possible with today's technology.
Okay, part 5, challenge 2, combusting fuel, or keeping the fire lit.
So our organism has successfully breathed in the air. Now we face the second battle, making sure the fuel actually eats and burns. And we hit a major bottleneck here. Because the air is moving incredibly fast, standard metal fuel powders literally clump up, a process called agglomeration. They clump into these heavy masses and just get spat right out the exhaust before they can release their energy. It's a huge problem. You're dealing with an intrinsic lack of oxidizer, standard fuels that just don't burn fast enough for supersonic airstreams, and these giant clumps that don't have enough residence time in the engine to finish burning. You're just wasting immense amounts of potential thrust. To fix this and force the fuel to ignite faster, engineers are basically hacking the fuel chemistry. They're replacing standard micrometer aluminum with highly reactive additives like magnesium and uncoated nanoaluminum. By swapping these into the baseline fuel mix, researchers are fundamentally changing how the fuel behaves. Magnesium, for example, has a very low ignition temperature. It lights up early, providing heat feedback to the rest of the propellant, which helps burn up those larger aluminum particles before they ever get the chance to clump together. Now, magnesium does solve the clumping problem, but there's a catch. It has a lower density, so it noticeably drops the overall specific impulse of the engine. But here's where it gets really clever. By injecting nanoaluminum into the mix instead, the data shows we maintain almost the exact same optimal specific impulse as the baseline fuel. Across the different mass ratios tested, the performance loss is practically zero. And it gets even better. Nanoaluminum increases the burning rate at 5 megapascals by nearly 3 times. 3 times! Let's put that into perspective. We've solved the agglomeration problem so the chunks don't clump, we've avoided losing our specific impulse, and now the actual ballistic burning rate jumps exponentially. Because these nanoparticles are so incredibly small, they release their energy rapidly, right into that supersonic airflow. We have successfully kept our metaphorical match lit in the hurricane. Finally, part 6, the future of flight beyond Mach 5. By optimizing that air intake and hacking the fuel chemistry with nanoparticles, we are genuinely solving the scramjet stool challenge. And the payoff for overcoming this immense complexity is huge. Like aviation pioneer Antonio Ferri pointed out, an air-breathing vehicle is just vastly lighter and more efficient than any traditional rocket because it doesn't drag heavy tanks of liquid oxygen through the sky. By mastering the intake temperature ratios and utilizing nanoaluminum for ultra-fast combustion, the dream of an air-breathing hypersonic vehicle is coming into very sharp focus. This leaves us with a pretty thrilling thought to wrap up our explainer. With engines that can now breathe Mach 4 air and instantly consume nanoaluminum, how soon will the extreme upper edges of the atmosphere become just another routine flight path? The math and the chemistry are proving that the barriers to sustained Mach 5 flight are not insurmountable. It's just a matter of precisely mastering that incredibly hostile supersonic airflow. Thanks for joining me on this deep dive, and keep your eyes on the skies.